We've just finished reviewing our energy definitions that we've learned previously, and we've also learned about enthalpy. Remember, enthalpy, that H, is just a measurement of the amount of thermal energy or heat in a system. So we're going to continue talking about that right now in a couple more ways. So first, on that left-hand side in the blue text, notice that breaking chemical bonds requires some input of energy. So if I want to pull apart a compound into its atoms, I need to add energy. So I need to add heat or thermal energy in order to break those chemical bonds and release that chemical energy. So you have to add in enthalpy. So your enthalpy right here, that H, is going to be greater than 0. On the other hand, in this red text, if you are forming chemical bonds, that's where your atoms tend to be more stable, is when they're forming those chemical bonds. Then notice that that will give off energy. So if you take various ions and you allow them to come together to form a compound, it is going to release energy. So releasing heat or thermal energy. Because of that, we say that that H value, that enthalpy, is less than 0 because it's releasing energy. That energy is leaving the system. When we talk about enthalpy for a reaction, we call this delta H right here in this cloud shape in the middle. When we're talking about delta H, that is the change of enthalpy over the course of the reaction. It is the enthalpy from the products minus the enthalpy from the reactants. So remember that your products, that is whatever you're forming, it's on the right-hand side of that chemical equation. On the other hand, on the left-hand side, you have your reactants. You can think of those as like your ingredients that the reaction needs. So products minus reactants. We have a couple of diagrams here. These are called enthalpy diagrams. So going along with our enthalpy, these are very important. We'll start with the one on the left. Notice that we have potential energy on the y-axis. We have that time on the x-axis. So as time is going on, there's some sort of reaction taking place. So first, notice our reactants. They're pretty low in that energy. You have to insert some sort of energy to get that reaction to occur. And then we have the energy of our products. In this case, the energy of those products is much higher than the energy of the reactants. What this tells us is that that delta H is going to be greater than 0. So if that delta H is greater than 0, we have to make up for that difference somehow. This energy is something that we have to add into the system. So we call this endothermic. Think endo, enter. We have to enter in some sort of heat or thermal energy in order for this reaction to take place. So endothermic, delta H is greater than 0. We're adding in energy so that this reaction can happen. Hopefully you also remember from biology, the value from where we start at reactants to where that reaction occurs at the top, that is a activation energy. So we have to put in some amount of energy for that reaction to start, and then it'll kind of slowly climb back down. But activation energy is what you need to get started. You may also remember from biology, you talked about enzymes. So in chemistry, we call them catalysts. A catalyst is anything that you can add to that system that's going to speed up that reaction. Remember that a catalyst, it speeds up that reaction by lowering the activation energy. So for example, if I added a catalyst to this reaction on the left-hand side, I may start with the same energy. Maybe it requires less energy to get that reaction to happen, and then I get to my products. So that decrease is due to that catalyst, so it'll make our reaction happen more quickly. Enzymes, they're just a really great example of a catalyst, but it is specifically a biological catalyst. It's a catalyst that you have inside of you. So you can use enzymes as an example if that helps you to remember it. On the right-hand side, this enthalpy diagram looks quite a bit different. We're not going to worry about the actual reactants and products that it lists. We don't really care about the names right now. We're just paying attention to that diagram. We still have that energy on the y-axis, and then time is on the bottom for the x-axis. They kind of showed you how it can happen in the forward direction and in the reverse, but we're not going to be too concerned with that right now. Notice that we start with some amount of potential energy. The numbers don't necessarily matter at this point. You go through your reaction, there's your activation energy right there. But then notice that your energy for your products is much lower than the energy for your reactants. What this tells you is this value, which it doesn't label, but about right there, that is going to be delta H, and notice that it is less than 0. It is going down. And because of that, that should tell you that you are going to be releasing energy through that reaction. So you still have to add in a certain amount of activation energy to get that reaction to start, but in the end, you are going to be giving off a net release of energy. So what we usually see if we do a reaction like this is something will be heated. So for example, if you're doing a chemical reaction and you have a thermometer in that solution and the thermometer, the temperature starts to rise, that should tell you that it is giving off heat. It is getting hotter. So chemical reactions where your temperature increases, that is an exothermic reaction. So heat or thermal energy is being released and exits the system. So think exo, exit. That energy is leaving the system. A great example of this is like a fire that's burning, it's giving off that heat. Fireworks also, chemical explosion that's happening, it's giving off heat. Those sort of things are exothermic reactions.